Hello everyone, I'm back with my first video that is related to robust control. I have started some videos on digital control, and as I promised also I want to put some robust control under my playlist controls. So hopefully my controls folder has sufficient topics for you if you are enthusiastic about control. Right now, there is linear control in it, state space control in it, a little bit optimal, a little bit non-linear, and my goal, as I said, is to add digital and what also robust control. And I also have a little bit of adaptive control in it. So this is my first attempt at putting a video that is related to robust control, and my goal is to put more. There are few videos left for digital control, and probably a few also for optimal and nonlinear. So I have not finished all of them really. Okay, my goal is to gradually add more and more to these control videos. So the topic today is called Generalized Bode Plots, or you might also call them Singular Value Bode Plots, or just simply Singular Value Plot. What is it? This is really good when you want to analyze a multiple input, multiple output system, MIMO, because most of the systems we have so far seen and talked about are SISO, single input, single output. Okay, but when your system has more than one input and most of the time more than one output, how would you analyze the frequency response of these MIMO systems? And in SISO, one of our most common tools for frequency response was Bode plot. So the question is, can we basically use these Bode plots for MIMO systems? Now that you don't only have a single transfer function, you have a matrix of transfer functions. Can you still do that? And the answer is absolutely you can. So let's go ahead and see how we can take care of that. So as I said, this idea revolves around the idea of singular values. And if you are not sure what singular values are or what is singular value decomposition, you can watch the video I have on my channel. If you just type in singular value, it brings you this video I have, which is around 38 minutes, and it's really useful for you. It explains that when you have a non-square matrix in general, that the matrix is not a square, singular value decomposition is basically a generalized version of eigenvalue decomposition. So the singular values are similar to eigenvalues, but they can be defined for a rectangular matrix as well. Okay, so you write your rectangular matrix as the product of three matrices. Two unitary matrices, U and V, and by that means UU transpose or VV transpose are just identity matrix, and a kind of semi-diagonal matrix. And by semi, I mean it doesn't have to be square, because diagonal, we define it really for a square matrix. So this is kind of semi. What does that mean? Means on this, if you define that line passing through 1, 1, 2, 2, 3, 3 as a diagonal, all of the numbers on that diagonal are called singular values, but you might have an extra row or several rows or several columns that are all zero. Okay, so that sigma matrix is, it has a similar dimension as your original matrix. And how many of these singular values you have? That's the minimum of m and n. So if you have 3 rows and 4 columns, then you only have 3 eigenvalues, right? In general, it's minimum of m and n, the number of non-zero values in this sigma. And the singular values do the same thing as eigenvalues. They show basically the directions, the eigenvalues are the magnitudes and the eigenvectors are the directions along which a vector is basically only scaled up or down, right, by those eigenvalues. So singular values is a general idea, okay, just like that, but more general. So if you want to generate these, what we call singular value Bode plots or generalized Bode plots, what are they, how do we generate them, and how do we interpret them. So here I'm gonna explain that to you, okay, how we do that, and with a single command in MATLAB. So the first thing is you need to have a matrix of transfer functions for your MIMO system, right? Let's say you have a matrix of transfer functions like this. So here your G is 2 by 2, which means your system, if your Y of S is basically G of S times R of S, then your R is basically, since this is 2 by 2, that has to be 2 by something, right? So let's say here you only have 2 by 1, and so your Y is also like 2 by 1, right? So 2 inputs and 2 outputs, okay? And then each one of these G's, you can replace their S's with I omega or J omega, right? Just like you did for a Bode plot. So you simply replace them with J omega or I omega. And once you do that, then at each specific frequency, each one of these components of this transfer function, each one of them will be a complex number, right? And so your transfer function will be a complex matrix. And this complex matrix, when you multiply it by any input, whether it's complex or not, it gives you a complex output. So this input will have some magnitude R, and this output will have some magnitude Y, and the question is, this Y is how many times this R, right? That is, if you remember, in frequency response is determined by what? Is determined by the magnitude of G of J omega. That is what we did in Bode plots. So we had a plot where it was magnitude of this complex number versus omega, and if you remember in Bode plot, right? So you remember the Bode plot, and if you forgot, please go ahead, and I have a lecture on the Bode plots, which you can see under my playlist control. So here you have omega, and here you have 20 log 10 of, let me write it a little bit nicer, 20 log 10 of magnitude of G of J omega, where the unit was in decibels, right? And basically, based on that, you can interpret the magnification, right? For instance, if this magnification is 1, then your number, the decibel of that is going to be 0. If this number is 10, then log 10 of 10 is 1 times 20, you get 20 decibel, right? If it's 0.1, that becomes -1, you get what? You get negative 20 decibel, right? So when you go down by 20 decibel, it means your magnification, right, or magnitude drops down by a factor of 10. And this is what we had in the Bode plot, okay? Again, if you want, you can go back and look at the Bode plot. But now the thing is, I don't have a single complex number right now, G of J omega. I have a matrix of complex numbers. So now what happens? And now your input is not probably one harmonic input. In this case, it has 2 components that might be harmonic, and your output also might have what? 2 components that are harmonic, okay? So here you have to get the norm of Y and compare it against what? The norm of R. And then see that norm of Y is how many times the norm of R. And the thing is, now that this is a matrix, you know, a matrix when multiplied by a vector, it can have 2 effects. It can scale it, it can rotate it, or both at the same time. If your input is in the direction of the eigenvalues of the matrix, then your output is just a scaled version of the input, and the scaling factor are the eigenvalues of the matrix. Otherwise, your input will be rotated and will be scaled at the same time. Okay? Yeah? Now, this G matrix, that was this eigenvalue and everything, it was good when G was a square, but G is not necessarily always a square, okay? For instance, if your input has 3 members and your output has 2, then you will have what? You will have here, G has to be a 2 by 3. So you're going to have 1 extra transfer function here and 1 extra over there. And if that's the case, then you cannot define eigenvalues for this 2 by 3 matrix, but you can define what? You can define those singular values, those sigmas that will sit in what? In this matrix sigma here, right? Those diagonals that will sit in the sigma matrix. Those will determine the amount of magnification, okay? And how many of them you have? As I said, it's the minimum of these 2. So if it's 2 by 3, you still will have 2 singular values. If it's 3 by 4, then you will have 3, and so on and so forth. So now that you have 2 magnification factors, sigma 1, let's say, and sigma 2, depending on in which direction your input vector is, it is going to be either scaled by sigma 1 or sigma 2 or somewhere in between, and also rotated. So your magnification, when you multiply inputs by this G matrix, is anywhere between what? Sigma minimum and sigma what? Maximum. So that's what you do. What you do is, now you let this omega change from some small frequency to some high frequency. At each omega, this G is a matrix. It could be in general a complex matrix, and this G will have a bunch of sigma, sigma 1, sigma 2, all the way to sigma n, or let's say starting from sigma what? Sigma min, all the way to some sigma max. And you're going to plot all of these sigmas versus what? Versus the omega that you used to find them. And that plot is exactly this generalized Bode plot that you can see here. So this is the frequency omega, and these are the sigmas. And since I have two sigmas, this is your sigma max on the top, and this is what? This is your sigma min. So for instance, at frequency of 10 to the 0, which is 1, you can see that the minimum magnification factor for this system is what? Is something like negative 18 decibel, and the maximum of that is somewhere around what? Somewhere around 5 decibel. And 5 decibel is 20 times magnitude, right? This is 20 times like 10 of magnitude of G for that frequency, and the same for this one, right? So this is like negative 18. And if you use MATLAB and calculate them, right, all you need to do is to basically divide 5 by 20 and raise 10 to that power. So 10 raised to the power 5 over what? 20. So you see your maximum magnification factor is 1.78, and the other one was negative 18, correct? So it is 0.13. So 0.13 and 178. Let's go and write them down here. So that means 0.13 magnification. Here that means 1.78. If your inputs are at frequency of 1 radians per second. If they are something else, then your magnification can change anywhere between these two numbers, and so on. So this plot that you see is called Generalized Bode Plot or Singular Value Bode Plot. And as I said, the most important thing is it shows you where is your minimum amplification, where is your maximum amplification. Your amplification is anywhere between these two. And one last thing that I need to emphasize again is if your output y is written as your transfer function times input r, which is the input to the system, the vector, and if you decompose g by u sigma v star, right, that's a typical singular value decomposition for any matrix, times r, what's the meaning of this? What's the meaning of that? The meaning is this. If your input vector r is in the direction of vi, the ith component of the secondary or right-hand side unitary matrix, then the magnification of the input to the output is exactly what? Sigma I. Look. And your output direction is exactly in the direction of what? Ui. And the same thing can be said about the other u's, v's, and sigmas. And if it's not in the direction of any of the vi's, then your output is not going to be in the direction of any of the ui's, and your amplification is going to be somewhere between these sigmas, depending on how close your input is to one of the v's. Depending on that closeness, that sigma related to that v is going to be the dominant sigma. Okay, but in general, whatever the amplification is, it's somewhere between sigma min and sigma max. Okay, this is the most important part of this plot. Okay, now how do we do it in MATLAB? In MATLAB, it's very simple. So let's say I want to create the generalized Bode plot for this 2x2 transfer function, all I need to do is to define the matrix, which you see here I have done. I defined the transfer function for S and then said G11 is 1 over S plus 1, 2 over S plus 2, 3 over that, and 4 over that. Okay, or you could simply use the transfer function of 1 and 1, 1, 2 and 1, 2, and so on and so forth. And then once you have these 4 individual transfer matrices, you put them in a matrix format like this, and you get your matrix of transfer functions for MIMO system. And the only command you need in MATLAB to use is the command sigma. Pass that matrix of transfer function to the command sigma, and that gives you this beautiful plot. Okay, we got this beautiful plot, everything great. Now, how do we interpret this? What's the meaning? We just define the meaning. Define that the magnitude of the amplification is anywhere between sigma min and sigma max. But you might say, what does it have to do with robust control? That's a very good question. And this is the part that it is related to the robust control. The spread of the singular values across frequencies can provide insight into the robustness of a system. Why? A large spread may indicate potential sensitivity to disturbance or modeling error. Why is that? And what does a spread mean? It means when the gap between the sigma max and sigma min is huge like that, this is a large gap, that means the difference between sigma min and sigma max is huge, but here the gap is small. So here the system magnification does not change significantly. For instance, here it might go from, let's say, 1.78 that we had to here, let's say this is below -40, so that's clearly below 0.01 or something, right? So this is, I don't know, maybe we can find it. Let's say this is -48, huh? So this is -48, and let's say this is 1.6, and this one here is around 20, so that's 0.1. And -48, let's do that one as well. So 0.004. So look at the difference. Your input at this range of frequency can be amplified or attenuated in this case because you're reducing the magnitude. The magnitude of it can be divided by 250, or it could be multiplied by a little bit less than 2. Look at how much difference you can get the output depending on the direction of the input. But here is anywhere between 0.1 and 1.6, and if it's narrower, then the amplification is even in a narrower region, right? So the wider the spread is, the bigger the gap between the min and max plot. It means that your output could be completely what? Different depending on the direction of it, right? Depending on this 2x2 inputs that you get. If it's 1, 2, you might get a magnification of, at that specific omega, right, at this omega, you might get an amplification of 1.2, but if, for instance, if it's, I don't know, 1 and maybe 1.5, guess what? You might get an amplification of, I don't know, 0.01. So you see, the system does not show robustness to the changes in the input. If the input changes, your amplification changes big time. And that is exactly the definition of lack of robustness. Because a system is robust if the output of it does not change big time significantly due to some changes in the input. And one of the most common sudden changes in the input that you cannot predict is a disturbance. A disturbance is a kind of random input out of your control. Or it could not be a specifically input error, it could be modeling error. Okay, if it's modeling error, then it could affect the input, or most importantly, it can affect this transfer function. And when the transfer function changes, these two plots would change as well. Okay, so your system will not be robust if you have too big of a gap between the min plot and the max plot for sigma. But if there are narrow distances between them, your system is more robust. Okay, so hopefully that makes a little bit more sense now, that why these generalized Bode plots are important for robustness analysis of a system. Okay, hopefully you enjoyed this video, and I will see you in my future lectures. Thank you so much. You have a great day.